Hi, this science highlight is about the Mango Nation project, which is funded under the NSF DASI program. I'm Elizabeth Kendall from SRI, and I'll be presenting with collaborators Asti Bhatt, also at SRI, Jonathan Makala at the University of Illinois, and Brian Harding at UC Berkeley. Mango Nation is a distributed network of all-sky imagers and Fabry-Perot interferometers measuring atomic oxygen night glow and neutral winds. These measurements enable investigations of plasma-neutral dynamics caused both by lower atmospheric and magnetospheric forcing across a range of spatial and temporal scales in the mid-latitude region. Mango Nation will be used to understand missing linkages in the thermosphere that enable energy and momentum transfer from the lower atmosphere to the ionosphere.
This project is motivated by three related science questions. The first, to investigate vertical propagation of thermospheric variability relative to effulgent dynamics. Second, to study the relative impact of lower atmospheric forcing with respect to magnetospheric forcing on the mid-latitude thermosphere and ionosphere. And third, to determine spatial scales of the lower and upper thermospheric winds. Now, these science questions primarily stem from what we still don't understand about the thermosphere, but they are also partly motivated from results from previous efforts that inspired this project. In this slide, for example, we see this figure from Mango network measuring 630 nanometer airglow. We see traveling structures in the F region images. The images are from different sites across the continental United States. And we see that the waves are propagating in various directions. Now, we speculate that the lower or the neutral atmosphere is influencing both the origins and the propagation directions for some of these traveling structures, but for others, the propagation is dictated more by the ionospheric electrodynamics. The challenge is that we don't currently understand what goes on in the region between the source and F region, namely the thermosphere and the mid-latitude E region. That is the reason why in this project, we are building a network of green line imagers combined with the FPIs measuring green and red line winds, which is going to be nested inside the pre-existing wider red line imaging network. Through this effort, we are also attempting to shed a better light on the relative influence of magnetospheric versus lower atmospheric forcing on the ionosphere-thermosphere. Mid-latitude provides an ideal setting to understand this because the time scales are slower and spatial scales are larger, which allows us to see a gentler interaction between these forcing. In this figure, again from the Mango network, we see how the mid-latitude F region reacts during a large geomagnetic storm. We can see aurora in the northern imagers and airflow depletions in the southern imagers. We hope that the combined capabilities of airglow and FPI networks will allow us to understand how deeply the magnetospheric drivers influence the thermosphere and how they will impact the plasma neutral dynamics.
So Asti just showed images from the ground, which shows a variety of waves propagating in different directions. From the imagers alone, though, all you can tell is what the apparent velocity of the waves is. And one of the advantages of our idea to co-locate FPIs with these imagers is to actually characterize the background wind in which these waves are propagating. This allows us to calculate not just the apparent phase velocity, but also the intrinsic phase velocity, which can give you some information on the vertical wavelength, for example. So people have been deploying these FPIs for many years, but to characterize and probe the neutral wind at using the red line, which gives you information about the upper thermosphere, and the green line, which gives you information about the lower thermosphere. So starting around 2012, 2013, we and others deployed a network of FPIs. So this is bring not just single sites, but bring them together to try to understand spatial characteristics of the neutral wind. In this graphic is shown the Nation network in the eastern US, as well as two FPIs that compose the Renoir network in eastern Brazil. So these were used to do a number of case studies, but one of the things we were actually able to do when we had cases where there were clear skies over our separate instruments at the same time, is to start to characterize the statistics of the spatial distribution. So under the assumption that the thermospheric wind is a random process, you can understand it in terms of its first order statistics, namely the mean or the climatology, and the second order statistics, namely the weather. So we did this in terms of the autocorrelation function. So if you get some fluctuation about the mean, some weather disturbance, how well does that disturbance correlate with itself for different spatial and temporal scales? So we did this here with nation data, and this is the plot shown below. The green dots indicate if you compute the site-to-site correlations based on the raw data, which is dominated by the climatology. So you can see that close by FPIs experience much the same climate. Even FPIs between the eastern US and eastern Brazil see climate that is somewhat correlated. But then when you remove the mean climatology and just look at the weather component, that's the blue dots, obviously the weather between the US and Brazil is totally uncorrelated. But nearby sites experience similar weather. It was clear after the study, though, that we were missing a lot of information in this gap between 1,000 kilometers and 7,000 kilometers. So this future deployment is targeting this gap by deploying sites that are a bit farther away from each other in this network. One of the other upgrades, major advantages since Nation and Renoir, we're planning to deploy these to the Western United States. The skies are a lot clearer there, so we hope to improve the data coverage by as much as 50% compared to Nation. So this is just one science topic. We of course also envision that this network can be used for many more case studies in collaboration with other instruments, maybe including other NSF DASI projects.
This figure shows a schematic of the Mango Nation instrument fields of view. The proposed network infrastructure will contain 3 types of instruments. There will be 10 5577 angstrom or green air glow imagers in the southwestern United States, forming a contiguous field of view spanning 15 to 20 degrees in latitude and longitude. There will be 3 FPIs with combined 630 nanometer or red and green capabilities. And finally, the project will augment a previously deployed network of redline imagers called Mango that extends across the continental US into northern Mexico. The new combined network will provide overlapping red and green air glow images between approximately 25 to 45 degrees north and 95 to 120 degrees west geographic regions, and also thermospheric temperatures and neutral wind fields from the 3 FPIs. The data products will be made publicly available through a project website, the Madrigal database, and an NSF-funded Integrated Geosciences Observatory, or NGO, collaborative platform. And software products will be available through a GitHub repository under an open source license. Our imager system was originally developed for the Mango project. It consists of an astronomy-grade camera typically used by amateur astronomers. It has a 35mm optical system designed to project an all-sky image onto a 2/3 inch CCD camera, and a 2nm bandpass filter centered at the desired wavelength. The camera enclosure is a self-contained weatherproof box designed for remote operation and requires minimal maintenance. We use commercial off-the-shelf components to create an economical imager system in a self-contained enclosure. This inexpensive instrument requires longer exposures to capture the same brightness levels as a high-end system. But since the airglow motion timescales are long, scientific accuracy is not sacrificed by the lower temporal resolution.
The FaviPro interferometer design that we will be using for this project follows the successful Mini-Me design that's been in operation at several sites around the world for the past decade or so. The design is shown in the middle figure here. It starts from the bottom with a deep thermoelectrically cooled CCD camera. Up from there, we have a lens that focuses the interference pattern created by a etalon system. This etalon system observes light that passes through a filter, a narrowband interference filter that isolates the atomic oxygen emission of interest. For this project, we had students at Cal Poly design a filter slider that would be able to choose between a red line filter and a green line filter so that the FPI would be able to observe the different altitude regions of interest. Above that is a sky scanning system that points the observing field of view in any arbitrary direction. Our typical observing pattern will be looking in the cardinal directions, as well as towards the vertical, and also towards a frequency stabilized helium neon laser to characterize our instrument functions. This instrument will be deployed in a dedicated trailer at the sites that are selected for deployment. The data that result from this instrument are observations of the thermospheric neutral winds made either at the red line or the green line emission. An example from a previous instrument is shown in the upper right. Here you can see the type and quality of data that we would expect from the FPIs that will be deployed. Typically, we observe uncertainties in the thermospheric neutral winds on the order of 5 or 10 meters per second. Below, we have an example of the sorts of data products that we can expect out of this project. With the multiple FPIs that are deployed as part of Mango Nation, we will be able to stitch together the data so that we can observe the thermospheric wind structure as a function of space and time. This example was created for a 2 FPI system deployment in Brazil. We would expect similar sorts of observations to be made with the 3 new FPIs that are deployed as part of this product.
So in summary, Mango Nation will create a distributed network of all sky imagers and for air glow and Fabry-Perot interferometers measuring atomic, oxygen, night glow, and neutral winds to enable investigations of plasma neutral dynamics caused both by the lower atmospheric and magnetospheric forcing. To follow progress on this project and view our data, you can already look at the deployed systems of Mango. Visit mangonetwork.org, and we'll keep adding instrument data as it comes online. We'd like to thank the NSF for funding through the DASI program, and thank you for viewing this science highlight.